All right, welcome back, everybody. We got Davis and Sophie here. Oh, okay. Can you see my face now?
Yeah.
Not that you really need to see it. By the way, I got a beard going here because Sophie wants me to grow one. I'm not sure how long that'll last. Anyway, hey, last week during our spring break, we did some experiments related to bubbles and surface tension of water. And it was really, really interesting to find out what we could find out about that. So I want to take a little time now to explain or summarize for my kids who have already been through this some interesting things about bubbles and surface tension. So we did a lot of different experiments and we're sort of tying them together in this little presentation. So we'll see how it goes. So today I want to talk to you about the physics of bubbles. Now, they exist because of a fascinating phenomenon called surface tension. We all love bubbles. I mean, everybody loves watching bubbles, especially big bubbles, bubbles in the bathtub. And have you ever wondered what allows them to exist? They seem so delicate, but they last longer than you think they would last, just floating around in the air, floating on the water. And I'm going to try to explain why certain bubbles can get bigger and last longer than others. So let's introduce this concept by showing you a penny in which we used an eyedropper to drop little dots of water on this penny. And I hooked up a little microscope to the computer and took a little video of what we were doing. So we took a penny and we dropped one drop at a time, drops of water on top of the penny. And how many drops do you think we could fit on that penny before the water started to dribble out to the side? I don't know. Just think to yourself. So when we did it, we got 21 drops to fit on the top of that penny before the water dribbled off to the sides. So as you see in that video, water behaves as though it is covered with this elastic skin. It's as though there's something holding the water in before the water spills out. And that's called surface tension. Now, the reason that happens is because of the shape of the water molecule. A water molecule has oxygen atoms and hydrogen atoms. Now, the oxygen atoms have what's called a negative charge. You'll learn when you're a little older about positive and negative charges. But the negative charge is the opposite of a positive charge. So the oxygen atoms have a negative charge, the hydrogen atoms a positive charge, and you may have heard the phrase opposites attract. Well, that's what happens in this situation. You have, with water, the positive hydrogen atoms are strongly attracted, particularly strongly attracted to the negative oxygen, negatively charged oxygen atoms. So what happens is, with water, when you're forming a bubble, all of the water atom molecules are sort of, when they're inside this space, they're pulled in all different directions, roughly equally, until they arrange themselves in a way in which these positive hydrogen atoms and negatively charged oxygen atoms link up around the perimeter of the bubble. Because at the outside of the bubble, there's nothing attracting the water molecules in this direction above the bubbles. On the edge of the bubble, all of the attraction is going on toward the center of the bubble. And that's what allows the hydrogen molecules to arrange themselves in this circular pattern. Now, The shape of the water molecule is key. When the hydrogen atoms and the oxygen atoms join together, they don't join in a straight line. One side has a positive charge and the other a negative charge. The molecules inside the bubbles are pulled in every direction until they reach a point at which the molecules on the outside of the bubbles are only pulled inward. And the result is that they quickly lock into place in the form of a bubble. So when we put individual drops with an eyedropper onto a penny, we counted 21 drops before the surface tension of the water on top broke. Now, I want to show you some video now of some giant bubbles we created last week. We've done this actually for several years. I'll show you the recipe to make it and how to make the apparatus to form them. But let me show you that video first, and then I'll explain a little bit more about the physics of bubbles. Okay, now, and this is how to make the giant bubble solution. You take 24 ounces of Dawn dishwashing liquid, and they say to not use Ultra, to use the regular, which is a lot harder to find. I use the Ultra anyway, and it seemed to work fine. So you have 24 ounces of that, and that's 3/4 of a quart. 24 ounces is 3/4 of a quart. As I said previously, you use this cotton clothesline. You have 3 gallons of water. You have to add that. And then this is the most important and weirdest ingredient. It is called J-Lube. And as you can see here, it says, a hand lubricant concentrate for veterinarian use only. Well, screw that. I got this on Amazon, and of course this is the essential ingredient for the giant bubbles. J-Lube is actually horse lube, and I won't say any more than that. But it's a powder. You use 1 tablespoon of this stuff, and you add it to the other ingredients. This is the magic ingredient that allows the giant bubbles to have great elasticity and to become very large before they burst. So you really need this. Put it all together in a bucket like this, and you get the results we'll show you in a little bit. Okay, to make the apparatus for making the giant bubbles, you take 2 carabiners here and attach them to 2 strings of clothesline. Cotton clothesline is what you're supposed to get. And I did 3 feet length on top, and then below it a 6-foot length of clothesline. And then you attach the carabiners to these dowels that have attached to the end, I think you call it a fisheye hook, that you just screw in the top. And then you attach these to the carabiners, and then you've got 2 dowels holding up each carabiner, and you lift up the apparatus after you've dunked it in the giant bubble fluid. Ooh, that was a good technique. Whoa, look at that. Look at that. Look at the colors. Ooh, nice one. Nice one. Ooh, another one. Whoa, look at that. Fantastic. Yeah, you gotta come right toward you. you may have noticed in the video of the giant bubbles how there were a lot of different colors that you could see on the surface of the bubble. It was really kind of amazing. There'd be, violet, orange, green, all of these different colors that were swirling on the surface of the bubble. And I want to explain why that is. So each bubble, this is pretty amazing, is about 1/100th of the width of a human hair. Take your hair, divide it up by 100. Take one of those pieces. That's about the width of the bubble. And what that means is it's about the length of one wavelength of visible light. You might know that light is a wave. It's actually, when you get a little older, you'll realize it's both a particle, it's made of particles and waves. But for now, we're just going to talk about the wavelength of light. When it travels in the form of a wave. So when light is hitting a bubble, the wave comes in, but when it hits the surface of the top outer surface of the bubble, some of the light bounces back, some of the light continues on, but the wavelength is changed. And so you have white light coming in, but because the bubble is not a uniform width all the way around, in some places it's thinner, in some places it's thicker, you end up with different wavelengths of light being reflected back. And even combining. When you have a wavelength of light like this, but then you have another one, I'll just use a different color to example. For example, like this, then they tend to either amplify or cancel each other out. And so by the combination of these different waves, you end up with different colors. So because the thickness of the bubble varies slightly all around it, it reflects light at different wavelengths that combine in various ways and produce the different colors. Now, I want to try to address the question, how can something that is so thin and delicate exist? And as I explained, it has to do with the water bubble, and in particular, an effect called surface tension. There was a fascinating story about the discovery of how adding soap to water, allowed the bubbles to get bigger before they broke. What was happening is that when you just pour water into a sink or into a bathtub, you might notice that there are a lot of water bubbles that form where the water, is splashing into the bathtub. But those bubbles are very small. They're very small because pure water, the attractive force of the water molecules is so strong that it breaks the bubbles up into smaller and smaller bubbles. So there was a scientist named Agnes Pockels back in 1891, and she decided to study how when you add different things to water, how does it change the surface tension? She actually invented a kind of a device to measure the amount of force it was needed to pull something off of the water when the water was combined with different materials. So she did a study of how different substances created different strengths of surface tension. She actually got this article published, but only because at the time there was a male scientist who vouched for her. At the time, women were not on their own allowed to publish scientific articles, but because a male scientist at the time saw this study as being so interesting, he vouched for her and got the article published. And she discovered that when you add soap to water, soap weakens the surface tension of the water. It breaks up the strength of this attraction and allows the bubbles to get larger before they break by weakening that surface tension. So with a bubble you make with water alone, the surface tension is stronger, so strong that it breaks itself apart very quickly. But adding soap weakens the surface tension enough to allow the bubble to live longer. And as I explained in the previous video, the J-Lube makes the bubble able to stretch even further. Now, last week, just coincidentally, to show you the power of surface tension, the kids and I were down at the local creek just walking around in our waders, and we would see water bugs. And what was interesting about the water bug?
They like ran on the water. They were like,
yeah, I'll show you a little video of what we found.
On the water.
Right, and these are bugs that actually walk on the water because they're light enough to not break the surface tension of the water. So they can walk on water in an interesting way. There's a water bug.
Tell me why.
He uses surface tension to stay above the water. Look at that bug just standing on the water with surface tension supporting him. He's walking on water. What is he, magic?
No, it's not matter.
Look at that guy. He's not really scared of me anymore. So now that we know that soap weakens surface tension and water seeks areas of stronger surface tension, let's show them the styrofoam boat propulsion trick that we did. Remember, we did the experiment where we put a little styrofoam boat in water, and then we added some soap behind the boat, and what happened?
It was like,
It shot forward. And that's because when we added the soap behind the boat, the surface tension behind the boat was less than in front of the boat. Water seeks stronger surface tension, so the boat was propelled forward as the water behind the boat sought out the stronger surface tension in front of the boat. Okay, now we've been demonstrating some principles of surface tension in various ways. Now, here's another way to demonstrate it. So here we have a little container filled with water. Not filled with water, but it's up enough to float a couple of these boats. We've got some dish soap,
Q-tip.
right? And I kind of carve these things out of styrofoam. Now they're supposed to act as simple. Yes, it does. It's aerodynamic. So I just took some styrofoam, carved it in the shape of a boat. Now I'm going to plop it in there. This is water. Of course, water has surface tension, and this is floating. Oh, there's a little wind here, but see if it still works. Davis, dip the end of that Q-tip in there. Now dip the liquid dish soap right behind the boat.
Please.
Did you see that? Try it again.
Can I try?
Yeah, Sophie can try next. Now, wait a minute. Before you try next, Sophie, let me explain what's going on. As we know from our bubble discussion, dish soap decreases the surface tension of the water.
And you can
Therefore,
also direct where it's going. This side,
right.
this side.
But let me explain this for a second. So when the surface tension is less behind the boat, it's greater in front of the boat. The water seeks higher, stronger surface tension. And so the water pushes the boat forward because it's seeking to go from the lower surface tension behind the boat to the higher surface tension in front of the boat. Okay, now, you all, let's show our viewers another fascinating characteristic of soap bubbles. What we did is, left to themselves, a bubble will be a perfect sphere because a sphere constitutes the least surface area of any given volume. If you wanted to put the same amount of stuff into different types of shapes, the most efficient way of doing that would be to put it into a sphere, because that's the least amount of surface area per volume of material you want to hold. So, but bubbles will also try to minimize their surface area when they are not allowed to be a perfect sphere. So if you force bubble film into a shape different than what would naturally occur, a sphere, some interesting dynamics occur. The bubbles will try to minimize their surface area in whatever shape they find themselves in, because they still want to stick to one another as closely as possible. So that means that if you put them in a cube, they do the following. I'm going to show you this video where I made a cube out of straws, and then I took each side of the cube, dipped it in bubble juice, the same bubble juice we use to make the giant bubbles. And the following effect occurred. Now, in the next demonstration, I'm going to use this plastic straw cube that I made. It's very easy to make. You can find a video showing the construction of it online. But basically you take bendy straws and you take one side. So here's one bendy straw attached to another one and another one and another one that makes a square. Then you put 4 wooden skewers, punch it through, connect it to another square of bendy straws. But before you add this, before you connect them, put straws on top of and over the wooden skewers. And then you connect them all together, you get this cube, and you can see what magic can be done with the exact same liquid recipe that we're using for the giant bubbles. Sophie, look. Sophie. I'll explain in the science class on Monday why that works. So, what's interesting is that the soap films form in a way that mathematically reduces the surface area as much as possible, regardless of the container they're in. So this dynamic is very, very hard to understand mathematically even today, even though we saw it in action. And what's interesting is that scientists are actually looking at the dynamics of bubbles to try to better understand black holes. Black holes have very high gravity attached to them. And what happens in areas of very high gravity can be similar to what happens in areas of very high surface tension and water molecule attraction. So they're trying to see if they can help explain how black holes work in areas of high gravity based on how bubbles work and how shapes change under conditions of very strong surface tension. So there you go. There's our little demonstration of the physics of bubbles and surface tension. And there was one quote I read by a guy named Lord Kelvin, one of the great Victorian era scientists. And he said, "You could study a soap bubble all your life and keep learning wonderful aspects of physics from it." And I think we just saw briefly, why that's so true. And anyway, hope you enjoyed it. We'll talk to you later.